Welcome to the Deep Dive, the show where we take your sources, your articles, your research, and really boil them down to the key takeaways, just for you. Today we're doing a deep dive into something that's, well, it's literally twisting and turning all around us, often without us even noticing. Think about a soil auger,
Yeah.
effortlessly digging into the ground, or maybe the drive shaft in your car, humming away, transmitting all that power. Both of these rely on a really fundamental mechanical principle. It's all about how things twist when you put a load on them. We're talking about torsion. So our mission today is to unpack the most crucial insights, maybe some surprising facts, and the practical applications from the sources we've got, giving you a real shortcut to understanding why this twisting thing matters so much in engineering and design.
Yeah, and by the end of this, you should have a really clear grasp of things like stress, deformation, and crucially, why engineers absolutely need to get how things twist to build anything strong and safe.
Okay, so let's cut right to it then. When we say torsion, what exactly are we talking about? How do our sources define it?
Well, at its core, torsion is simply a moment. A rotational force that tries to twist an object around its long axis, its center line. It's basically the material fighting back against being turned.
Ah,
And you see it everywhere, like in those heavy-duty drive shafts in cars and machinery, transmitting all that rotational force.
right.
Or, like you said, a soil auger.
Oh,
That thing is under constant, significant torsional stress as it chews through the earth.
So it's really about that internal resistance to being twisted. I heard there's a good way to picture this. Something about a rubber shaft.
Oh, yeah, absolutely. It's a great analogy. Imagine a perfectly round bar made of something super flexible, like rubber. Now, if you draw straight lines along its length, right,
Mhm.
and then twist one end while holding the other,
Mm-hmm.
those straight lines, they don't stay straight. They actually warp into a spiral, a helix shape.
Okay.
But here's the really crucial bit. Even with all that twisting, the circular cross-sections, the flat ends, if you like, they stay perfectly flat. They don't bulge or warp.
That's interesting.
And any radial lines you draw on those ends, they stay straight too. They just rotate around. This no-warp thing is surprisingly important because it makes the math so much simpler for circular shafts, a luxury we definitely don't have with other shapes, as we'll find out.
Right.
And, for small twists, which is often the case in engineering, the shaft's overall length and its radius, they basically stay the same.
Yes, that's a helpful visual.
Yeah.
So when you twist one end compared to the other, that amount of rotation of a radial line, that's the angle of twist.
Precisely. We call it fight.
And I'm guessing that angle gets bigger the further you are from the fixed end.
You've got it. And this angle of twist is directly linked to something called shear strain, represented by or gamma. Think about a really thin slice, like a coin, out of that shaft. The tiny difference in rotation between the front face and the back face of that coin, that's what causes the shear strain inside the material. And here's where it gets really interesting. This shear strain, it's not the same everywhere across the slice. It's actually 0 right in the middle at the shaft's axis, and it increases linearly as you move outwards, reaching its maximum value, max, right at the outer surface. This linear increase is absolutely key.
Okay, so if the strain changes linearly, then for most materials engineers use, the stress must follow that same pattern. 0 in the middle, max on the outside.
Exactly. For materials that follow Hooke's law, what we call linear elastic materials, the shear stress, tau, mirrors that linear strain pattern. That is go where G is the shear modulus.
Right.
So 0 stress at the axis, maximum stress max at the outer surface. To actually calculate this, we need a crucial property of the cross-section's shape. It's called the polar moment of inertia, or just J.
J, okay.
Yeah, J basically tells us how much the shaft's shape resists twisting. Bigger J, harder to twist. It's measured in units like millimeters to the 4th power.
And with that, J, we get to the main event, the torsion formula. This lets us calculate the actual shear stress caused by the internal torque, T.
That's the one. The maximum shear stress, tax, which happens at the outer surface, radius C, is tac max word TCJ.
DCJ, got it.
And if you want the stress at any radius inside the shaft, it's just cac TJ.
So it scales linearly with the radius.
Exactly. But remember, this formula works best under specific conditions. The shaft needs to be circular, solid, or hollow,
Right.
made of a homogeneous material, and behaving linear elastically. The stress itself acts tangentially perpendicular to the radius on that cross-section. And interestingly, there's also an associated shear stress acting along the length of the shaft.
Ah, and that connects to something I found in the sources about wood shafts splitting lengthwise.
Oh yeah, that's a fantastic point. Wood is anisotropic.
Meaning,
Meaning its properties aren't the same in all directions. Its shear strength parallel to the grain along the shaft's length is much, much weaker than across the grain. So when you twist a wooden shaft hard enough, that longitudinal shear stress finds the weak path along the grain and pop. It splits. Very different from steel.
that makes sense. So for someone listening, if they need to figure out the stress in a shaft, what's the step-by-step?
Okay, for basic analysis, think 3 steps. 1, internal torque, T. You conceptually cut the shaft where you're interested and use equilibrium sum of moments is 0 to find the internal twisting force, T2. Section property, J. Calculate that polar moment of inertia. For a solid circle, it's J with 2 C4, where C is the outer radius.
Yeah.
For a hollow tube, it's J times the difference of the outer radius to the 4th power and the inner radius to the 4th power. So co 4 A soy.
Right, outer minus inner, both to the power of 4.
Yep. And 3, shear stress. Plug T, J, and the radius C for max for intermediate into the torsion formula, legit TJ mix max TCJ. Just make sure your units are consistent. Newtons, millimeters, megapascals, that sort of thing.
Okay, clear. So we can calculate the stress. How does this connect to, real-world stuff like transmitting power?
Yeah.
Like in a car engine or factory equipment?
Ah, great question. That's where it gets very practical. Power, P, is basically work done per unit time. For something rotating, power is the torque. T times the angular velocity.
T equals T omega.
PT, exactly, where 4 is in radians per second. Torque is often Newton meters, so power comes out in watts, or, horsepower in some contexts. 1 horsepower is about 746 watts.
And sometimes angular velocity is given in frequency, right? Like hertz or RPM.
Yeah, good point. If you have frequency F in hertz, cycles per second, then O equals 2. So the power equation becomes P equals 2pt.
Okay.
And this is fundamental for shaft design. If you know the power you need to transmit, P, and the speed it needs to rotate at, O or F, you can figure out the required torque T. Then if you know the maximum allowable shear stress for your chosen material, allo, you can calculate the required geometric property, which is JC. So JC to allo.
Ah, so that tells you how beefy the shaft needs to be geometrically.
Exactly. For a solid shaft, since JC depends only on the radius C, this calculation gives you a specific required radius or diameter.
Makes sense.
For a tubular shaft, it gives you a relationship between the inner and outer radii. This offers more design freedom. You could choose an outer diameter to fit a bearing, then calculate the required inner diameter, maybe saving some weight.
So, quick example. If I need a steel shaft for a motor, maybe 5 horsepower, running at 175 RPM, and the steel's allowable stress is 100 MPa, I could actually calculate that I'd need a diameter around 22 millimeters.
Precisely. That's exactly how engineers use these principles to size components.
Cool. Now let's circle back to that angle of twist. How do we actually calculate the total twist from one end of a shaft to the other, especially if things aren't constant?
Right. Well, the most general way, if the torque T, the cross-section J, or even the material G changes along the length, you actually have to integrate, is the integral of Tx gx along the length.
Okay, calculus. But what about the simple case?
Thankfully, the most common case is where T, J, and G are all constant along the length L. Then it simplifies beautifully to TLJG.
TL over JG. That looks familiar.
It should. It's very similar in form to the formula for axial deformation of a rod, PLAE. Same idea. Load times length over stiffness times geometry.
Elegant. And I guess, like with forces, we need a sign convention here. How do we know if the twist is positive or negative?
Absolutely crucial. We use the right-hand rule again. Point your right thumb outward along the shaft's axis. The direction your fingers curl indicates the positive direction for both torque T and the angle of twist.
Okay, thumb out, fingers curl positive.
Stick to that consistently, especially when you have multiple torques. If a torque acts in the positive direction, it causes a positive twist. If it acts opposite, it causes a negative twist.
So what if you have a shaft with, say, gears applying torques at different points? Or maybe the shaft diameter changes partway through?
Simple. You just break the shaft down into segments. Within each segment, T, J, and G should be constant. You calculate the twist, phi, TLJG, for each segment using the internal torque in that segment.
And then just add them up.
Exactly. You algebraically sum the twists from all the segments. Hey, TLJG. Be careful with the signs based on the right-hand rule.
So if I had, say, a 200 millimeter steel shaft with torques applied at ends A and D, and maybe another one in the middle, I could find the twist of end A relative to end D by calculating the twist in each section and adding them.
You got it. And what's really cool is once you know that total angle of twist, you can figure out how much something physically moves. Like if there's a gear on end A and you know phi, You can calculate how far a tooth on that gear moves.
Wow, okay. From angle to actual displacement.
It's fundamental for precision machinery.
Now, this is where I think it gets really interesting. Sometimes, just looking at forces isn't enough, right? What if a shaft is fixed at both ends? You have reactions at both ends, plus maybe an applied torque. Too many unknowns for simple equilibrium. That's statically indeterminate.
That's the term. Classic engineering problem. When equilibrium equations alone, like mellow equals 0, don't give you enough equations to solve for all the unknown torques or reactions, the structure is statically indeterminate.
So how do you crack those?
You need more information, essentially another equation. We get this from compatibility, how the displacements or rotations must fit together. So the process has 3 parts. 1, equilibrium, still start here. Draw your free body diagram, write the moment equilibrium equation. You'll have more unknowns than equations. 2, compatibility. This is the key. You look at the constraints. If a shaft is fixed at both ends, say A and B, then the total angle of twist from A to B must be 0. Phi B equals 0. That's your compatibility condition. It relates the rotations caused by the different torques.
Okay. The geometry dictates a relationship between the twists.
Exactly. 3, load displacement. Now you use our angle of twist formula, phi TLJG, to express the twists in that compatibility equation in terms of the unknown torques. Now you have enough equations, equilibrium plus compatibility, expressed via load displacement, to solve for the unknown torques.
So for that shaft, fix at both ends with a torque in the middle. I'd write the equilibrium equation, then write that the twist from one end to the other is 0, expressing those twists using TLJG for each section, and then solve the system.
Perfect. That's the procedure. It lets you find those reaction torques at the fixed supports. And this method is also vital for composite shafts. Say, a steel tube bonded to a brass core. They're twisted together.
How do they share the load?
Well, the compatibility condition is that they must twist the same amount because they're bonded, steel for brass. But using the load displacement relation, pre-TLJG, since steel has a higher shear modulus G than brass, for the same twist, the steel must carry a larger internal torque T and thus higher shear stress.
So the stiffer material takes more stress.
Generally, yes. You often see a jump, a discontinuity, and shear stress right at the interface between the two materials because their G values are different.
Okay, we've spent a lot of time on circular shafts. They seem relatively well behaved. But what happens with non-circular shapes, like twisting a square bar?
Now things get significantly more complex. The big difference: non-circular cross-sections warp. They bulge out or distort when twisted. Those nice flat cross-sections we saw on the rubber cylinder, gone.
They don't stay flat?
Nope. And because they warp, our simple TJ formula doesn't apply directly. The analysis comes from a much more advanced theory of elasticity. And here's a really surprising fact from that theory. For a twisted square shaft, the shear stress at the corners is actually 0.
0 at the corners. Why?
Because, think about the outer surface. There can't be shear stress acting perpendicular out from a free surface. And because shear stresses on perpendicular planes must be equal, complementary shear, the stress in the cross-section at that corner point also has to be 0.
Huh. Weird. So maximum stress isn't at the furthest point, unlike a circle.
Right. For a square, the maximum shear stress actually occurs at the midpoint of each flat side.
Okay. But even with all that complexity, the sources emphasize something important about efficiency.
Absolutely. For a given amount of material, cross-sectional area, and a given applied torque, the shaft shape that results in the lowest maximum shear stress and the smallest angle of twist is always a circle.
So circular is best for torsion, generally speaking.
Structurally, yes. But sometimes you need other shapes. For common ones like squares, triangles, ellipses, engineers use specific formulas, often found in tables or handbooks, derived from elasticity theory to find max and phi. Then there's another important category: thin-walled tubes with closed cross-sections. Think aircraft fuselages, bike frames, lightweight structures.
Okay. What's special about them?
We use the concept of shear flow, denoted Q. It's the average shear stress of G in the wall multiplied by the wall thickness, Q arc dot G.
Shear flow Q.
And what's fascinating and incredibly useful is that for a closed, thin-walled tube under torsion, this shear flow Q is constant all the way around the tube's perimeter.
Constant flow, even if the thickness changes.
Even if the thickness changes, which leads directly to a key insight. Since Q is constant and Q of GT, the average shear stress, Ta of G, must be highest where the thickness T is smallest.
So the thinnest part of the wall sees the most stress.
Exactly, your potential failure point. The formula for average shear stress is TABG equals T to TAM, where T is the torque, T is the thickness at that point, and AM is the mean area enclosed by the center line of the tube's wall.
T over 2T.
Yep. And there's a related formula for the angle of twist, which involves integrating the reciprocal of the thickness around the perimeter.
So for a thin rectangular tube, if the top and bottom walls are thinner than the side walls, even though the shear flow is the same everywhere, the stress will be higher in those thinner top and bottom walls.
You've got it. Perfect example.
Okay, now let's talk about places where things can get a bit dicey. Sudden changes in shaft shape, stress concentrations.
Right. These are the hot spots. Anywhere you have an abrupt change in geometry, like a step where a shaft goes from wide to narrow, or around a keyway cut for a gear, or near a coupling flange, the stress distribution gets distorted. The simple torsion formula doesn't capture this. The actual maximum shear stress right near that discontinuity can be significantly higher. We quantify this using a torsional stress concentration factor, K. You calculate the stress in the smaller section of the shaft using the standard formula, TA Shear, and then multiply it by K. So max equals K, TCJ.
And where does K come from?
Usually from experiments or detailed simulations presented in graphs or tables in engineering handbooks. K depends on the geometry, like the ratio of the shaft diameters, DD, and the radius of the fillet used to smooth the transition.
And I bet making that transition smoother, like using a larger fillet radius R, reduces K.
Exactly. Or making the jump in diameters, DD, less abrupt. Good design practice involves generous fillet radii to reduce these stress peaks.
Why does this matter so much?
It's absolutely critical for two main scenarios. Shafts made of brittle materials, like cast iron, which can fracture suddenly at these stress peaks, and any shaft subjected to fatigue loading repeated cycles of twisting.
Fatigue. Like a car axle.
Perfect example. Those repeated stress cycles, even if below the yield strength, can initiate a crack at a stress concentration, which then grows over time until failure.
But what about regular steel under just one big twist?
For ductile materials under static, non-repeating loads, stress concentrations are often less critical. If the stress at the concentration point reaches the yield strength, the material just yields locally and redistributes the stress a bit more evenly. The overall shaft doesn't necessarily fail.
Okay, so K is vital for brittle materials and fatigue, less so for static loads on ductile ones. Makes sense. So what happens if you really crank on a shaft, push it beyond its elastic limit so it permanently deforms? What do the sources say about that?
This is getting into inelastic or plastic torsion. It's pretty interesting. Even when the material starts to yield, the shear strains still vary linearly from the center zero to the outer surface maximum. That part doesn't change.
Strain is still linear, but stress isn't.
Right. Once the shear stress at the outer surface hits the material's yield strength, that outer layer yields. As you apply more torque, this yielded region grows inwards, like a ring expanding towards the center. You end up with a plastic annulus on the outside and an elastic core in the middle that's still behaving elastically.
Elastic core, plastic annulus.
Okay. The torque required to just start yielding is Ty. As you increase the torque further, you get this mix of elastic and plastic zones. Now, the absolute maximum torque the shaft can possibly handle is called the plastic torque, TP pi. This occurs when the entire cross-section has yielded. The shear stress is essentially Twy everywhere across the section.
Fully yielded. And the sources mentioned a specific number for how much bigger TP is compared to TY.
Yeah, it's quite significant. For a solid circular shaft, the plastic torque TP is 43 times the maximum elastic torque TY. So it can handle 33% more torque once it fully yields compared to when it just started yielding.
A 33% safety margin built in, sort of, once yielding starts.
In a way, yeah, in terms of ultimate torque capacity. But now for the really interesting bit. What happens when you remove that big plastic torque TP?
Does it just spring back?
It tries to spring back elastically. Imagine the stress distribution for TP, uniform Y. Now imagine applying an opposite torque elastically that's equal in magnitude to TP/AP. The material recovers elastically based on that linear stress distribution we saw earlier. When you superimpose that elastic recovery stress, which varies linearly, onto the uniform plastic stress, they don't perfectly cancel out. You're left with residual stress.
Residual stress. Stress left inside even with no load.
Exactly. The outer fibers, which were yielded the most, end up with a residual stress acting in the opposite direction to the original torque. The inner fibers have residual stress acting in the same direction. It's a locked-in stress pattern.
Wow. So the shaft remembers being overloaded.
In a sense, yes. And this raises a really important question for you, the listener. How might this hidden locked-in stress affect how that shaft behaves later? If it gets loaded again, or if it's subjected to fatigue, it changes the starting point for stress calculations.
What a fascinating journey we've taken. We've twisted our way from, the basics of how a shaft deforms, through calculating stresses and angles, power transmission, then into these more complex areas like non-circular shafts, thin tubes, stress concentrations, and even this idea of plastic deformation and residual stress. It really highlights how crucial understanding torsion is for designing, well, almost anything that rotates or resists twisting, from simple tools to complex machines.
Absolutely. And the key things for you to remember are circular shafts are generally the most efficient for torsion. Non-circular ones warp, making things trickier. Watch out for stress concentrations, especially with fatigue or brittle materials. And understanding what happens beyond the elastic limit, including residual stress, can be vital for predicting long-term behavior and durability.
So, thinking about that residual stress left behind after a major overload, what implications could that have? Consider, say, components in aging infrastructure, like a bridge support, or maybe even a spacecraft part that got hit by unexpected debris. How might that hidden, locked-in stress affect its long-term integrity, its fatigue life, or how engineers analyze its potential for future failure? Something for you to mull over.